so let me do the second exercise. Okay, so let me go back and figure out, like what was the second exercise, So I gave y double dot t plus yt equals u of t, right? So let's do this problem. Y double dot t plus y of t equals u of t. Okay, so that's the second problem. So so once again you can see that it's a second order system, and if we take the Laplace transform and apply zero initial conditions, what are we going to get? So let's follow the same steps. So take the Laplace transform on both sides. Okay, of course I'm going to skip a few steps because by now you know what to do, right? So if you take the Laplace transform on both sides, once again please write down the complete transform of the derivatives, like do not substitute the initial conditions to be 0 in the first step itself, because you never know. Okay, in some problem initial conditions may not be 0, right? So we need to be a bit careful. So always write down the entire expansion. Okay, now in order to find the transfer function, take all initial conditions to be 0, right? Because that is the definition of the term transfer function, right? So this implies that y of s divided by u of s will be equal to 1 divided by s squared plus 1, right? That's what we will get. If I take all initial conditions to be 0 and I collect terms involving y of s and cross multiply, this will be the planned transfer function p of s. Okay. So now what can I comment? What are the values of n and m? What are n and m here? N is 2, second order system. M is 0. What about poles? Yeah, you solve s squared plus 1 equals 0. So this implies that s is going to be equal to, of course, we are going to use j. You could use I also, but as I told you, we are going to use j in this particular course. Okay, so we will essentially say it's plus or minus j. So zeros there are none once again. So if you plot the S plane and mark these two poles, where are they going to be? They are going to be at plus j and minus j. Okay, so those are the two poles, okay, for this particular system. Yes. Which one?
This plus j as a real part can be anything.
Real part is 0. See, s squared plus 1 means s equals plus or minus j. So your real component of that solution is going to be 0, right, isn't it? See, if you substitute any real component, if you say c plus or minus j, where c is any real number, can you satisfy this equation? Please try. Okay, you can't, right? So that's why the solution is we take it to be plus or minus j, right? Okay, so we can try it out, right? Let's see. Since this question has been raised. Let me also work it out. Okay, so let's say we take it as c plus or minus j. Is that your point, right? So c being any real number, let's try it out. So if I have c plus or minus j, let's say we take c plus j, right? At least one solution plus 1 whole squared. So what I'm going to have? I'm going to have c squared plus 2cj plus j squared plus 1 equals 0. So I'll have c squared plus 2cj equals 0, right? So this will be satisfied only when c is identically equal to 0, correct? So that's why we are taking plus or minus, right? So the real part is anyway 0. Okay, of course, let me put it in a box so that, like, see, yeah, whatever I am drawing like this, like are asides, right? So yeah. Okay, so that's plus or minus j, right? Those are the two roots for this one, right? So what we are having is that, like, we are having what are called as complex conjugate poles, right? We are essentially having a purely imaginary poles here. Okay, correct. So what do we do for the unit step response, right? So we need to get the unit step response. How do we get this? Unit step response means u of s should be equal to 1 by s, right? So then y of s is equal to p of s times u of s. See, this is the advantage once we find the transfer function is that like we can find the system output for any given input, right? So that's an advantage, right? So p of s is going to be 1 by s squared plus 1. So I have 1 by s times s squared plus 1. So now what do I do? How can I simplify this? Bs plus c divided by s squared plus 1, right? So I can do a by s plus bs plus c divided by s squared plus 1, right? So immediately we see that what is going to be a? It's going to be 1, right? And if you solve for b and c, what are you going to get? Minus 1 and 0, right? So we will have essentially s divided by s squared plus 1. Okay, I am sure by now we have done a few examples. By now I am sure all of you will be familiar with how to calculate these residues, right? I think last week we did a few cases, right, where I showed you how to do even for second order terms and so on, right? Yeah. So once we get this, you know, like so this implies that y of t. Wait a minute, did I give you this example, right? Yeah. Okay, great. So y of t is going to be equal to 1 minus cos t. Do you agree? Okay. So that's my step response. So, but then like if we want to make the same observations as before, right? So what happens here? Let us say I want to make the same observations as before, right? So what happens as t tends to infinity? Y of t tends to what? Of course, essentially it oscillates, but is it bounded? Okay, so let me say y of t, at least the magnitude of y of t, right, remains bounded. All right, so that's something which we can say. So using this, see, once again, step is a bounded input, right? Is it not, right? So we are getting a bounded output. So from this, would you conclude that the system is Bibo stable? No. Why not? We don't know about all inputs, right? So that's something which we need to check out. And by the way, like where are the exponential terms here? You could use Euler's relation. So please note that the general viewpoint even still works out, right? So see, I wrote that in general real part of the poles would appear, okay? Some people will write the poles would appear. Okay, so that's why I just wanted to make a distinction, okay, because see, if I write poles would appear, you know, like yes, that's also correct, but then like you see that, you know, like in this particular problem, you know, like the real part is 0, so you don't need to necessarily have exponential solutions appearing all the time. It's implicit, it's contained within the cos and the sine, okay. So we could say that exponential terms will have the real part as exponent. If you have complex conjugate, you will get cos and sine. You could also write this as y of t as, using the Euler's relationship, as what is cos omega t, e power j omega t plus e power minus j omega t by 2, right? So here omega is 1. So we are correct in even like writing the solution as e power t plus e power minus t by 2. Sorry, jt, right? Sorry. Okay. So you see that now the poles are appearing as, once again we are going to have two exponential terms, you know, like corresponding to two poles, right? The exponents are the poles themselves, right? So both interpretations, I am just writing this way, right? Both interpretations could be derived, okay, out of this exercises, okay. So you see that the poles are there, right, as the exponential terms. So, but if you have complex exponentials, you know, you can write as cos and sine, right, using the Euler's relations. So that's why I told in general, you know, like we could also look at, for our purpose, you know, like we could look at the real parts being the exponents, right. In this particular term, 1 minus cos t, you don't have an explicit exponential term because the real parts of the poles are 0. Okay, so that's why you have this. Is it clear? Okay. Now, what I want you to do, remaining on this problem, we will go to the next problem shortly. I am just renumbering. Okay, so please do this. So I just changed only one thing, right? So instead of y double dot t plus y of t equals u of t, I just changed the transfer function to be y double dot t plus y dot t equals u of t, right? That's the difference between problems 1 and problems 2 and 3, right? So now can you repeat the same process? So what would be the planned transfer function? Please take the Laplace transform on both sides, take initial conditions to be 0, get the ratio of y of s and u of s. What would you get? You would get 1 by s squared plus s, right? So this I can rewrite as 1 divided by s times s plus 1. So similarly, I can say n is equal to 2, m is equal to 0. What are the poles? The poles are at 0 and minus 1, correct? And there are no zeros. Okay. So consequently, what will happen? I will have this. Okay. So where are my poles here in this example? In the S plane. I have a pole at the origin, I have a pole at minus 1. Okay, so these are my 2 poles. So please find the unit step response and let me know what do you get.
Sir,
Yes?
for the previous question, y of t is 1 minus cos t.
Mm-hmm.
Why is that not Weber stable? It's Weber stable.
Is it?
It should be because it's bound for any
Ah,
constant input.
that's exact. Okay. So we'll answer that. I'm going to generalize by doing this problem. Okay. Let's please hold on for a minute. Okay. The question was that, like, I neither said that it's Bibo stable or nor said it's unstable, right? As far as Bibo, I only said we need to do further analysis, right? Which will become clear, right? Yeah. So, but to give you the answer, you know, like it's a tricky question. You know, like it depends on whom you talk to. Okay. That's why I'm doing things carefully. Okay, step by step. Okay. So let's unit step response, please. You know, like, so unit step response means u of s to be is 1 by s. So y of s is what is this? P of s times u of s. That's going to be 1 divided by s squared times s plus 1, right? Because we have a 1 by s multiplying this one. So what are we going to get? We are going to get a by s plus b by s squared plus c divided by s plus 1, right? That's going to be our partial fraction expansion. So what are a, b and c? C I can get as 1, right? B I can get once again as 1. Am I correct? So a, you can substitute any other value you want, and if you simplify, what will you get? Minus 1. Is that correct? Okay. So now what happens to y of t? We get minus 1 plus t square t, right, plus e power minus t. So this is the unit step response. Okay, previously also there was a unit step response, right? So now what can we observe? So let's observe. So what do you think happens to the magnitude of y of t as t tends to infinity? What happens to its magnitude? It tends to infinity. Why? Right? Because I have a t term, right? So once again you see that the solution has exponential terms. The poles are the exponents, right? So the poles are at 0 and minus 1. So what is e power 0? It's just like what to say 1, right? So that's why you have a term like that. And then like you also have e power minus t, minus 1 also comes in, right? But in addition you have a t term, okay, which essentially tells you that the magnitude of the output is going to go to infinity, right, as time tends to infinity. So would you call this system as Bibo stable? Yes or no? See, what is Bibo stable, right? So let me recap the definition very carefully. Okay, each and every word is very what to say important. A system is said to be Bibo stable if the output remains bounded in magnitude for all time given any bounded input. Okay, the keyword is any or all bounded inputs, right? So here, if you want to show something is not Bibo stable, you just need to find one bounded input for which the output is unbounded. Is it not? See, in fact, in life, showing that something doesn't work or is not true is easier, right? Because you just need to have only one case where it doesn't hold true, right? And for this particular system, have we not found one bounded input for which the output is unbounded? We have, right? So for this particular system, we have found a step input for which the output is unbounded, okay? Now the question is, would you call this as unstable or something else? Okay, we'll see what that something else in the afternoon. Okay, so after doing a few more examples. Okay, so just hold on. Okay, so we would see that, you know, like there are some more examples that we need to do before we can generalize. Okay, yeah. Okay, so I hope the flow is clear, right? So as the fourth example, let's do this problem. Okay, so y double dot t plus what did I give you there? Y dot t minus 2ut, 2yt equals u of t. Right. So what is the plant transfer function p of s here? So it's going to be 1 divided by s squared plus s minus 2. Okay, I'm assuming that all of you can follow with me. Please stop me, okay, if anything is unclear, right? Yeah. So this I can rewrite it as 1 divided by s plus 2 times s minus 1. Am I correct? Is that correct? Right? So once again, you know, like we can see that n equals 2, m equals 0. The poles are at minus 2 and plus 1. Zeros, there are none. So if I draw the S-plane for this particular example, okay, the poles are going to be at minus 2 and plus 1. Okay, so this is the left of complex plane and this is the right of plane. Okay, so what is the step response, unit step response? Unit step response means u of s is going to be equal to 1 divided by s, right? So if u of s is 1 divided by s, y of s is going to be equal to p of s times u of s, and what are we going to get? We are going to get 1 divided by s times s plus 2 times s minus 1, right, which is going to be a by s plus b by s plus 2 plus c divided by s minus 1. Okay, so what are the values of a, b and c? A is going to be minus 1 by 2 or plus 1 by 2? Minus 1 by 2, right? So, and then what about B? We are going to get 1 plus 1 by 6, right? And what about C? Sorry? 1 divided by 3, right? Okay. Am I correct? So, those are the 3 partial fractions. So, this implies that y of t is equal to minus 1 by 2 plus 1 by 6 e power minus 2t plus 1 by 3 e power t. Okay. So, now we immediately note that as t tends to infinity, what happens to the output? The magnitude of y of t tends to infinity, right? So, that is what happens here, right? Is it done? Right? So, we can immediately see that once again there are 2 exponential terms. The poles appear as exponent, or the real parts appear as exponent, because anyway the poles are real here. So, you could see that minus 2 and plus 1 are the 2 poles. You could see them appearing as exponents. But then you see that as t tends to infinity, the magnitude tends to infinity. Why? Because we have e power t, right? The magnitude of e power t tends to infinity. Okay, so that's why this blows off, right, to infinity. Now the question is, given this unit step response, like would this system be bibostable or unstable, right? So once again, like we would figure out the answer, right? So what we are essentially getting at is the following. Okay, so before you come to afternoon's class, anyway you have time, right? So I want you to do this example. Okay, take problem number 2, y double dot t plus y of t equals u of t. Okay, please take that problem. Okay, so as problem 5, consider y double dot t plus y of t equals u of t. Okay. Now find y of t when, let's make our life simpler, like let's say I give you u of t to be equal to, let's say, cos t. Okay. Please take, find y of t when u of t equals cos t. Similarly, as the 6th problem, I am going to give you this. Take the 3rd problem, y double dot t plus y dot t equals u of t. Find y of t once again when u of t is cos t. Okay. So please do these problems. Okay, and you come and tell me what you observed, and then like we would continue our discussions from here in the next class, right? So I hope it's clear what I want you to do, right? Take problems 2 and 3. For both problems, we figured out the unit step response, right? Now I want you to figure out what is the response of the system or output of the system when we give a cosine input, right? As cos t as the input to the particular system. Okay, do the same exercise, take inverse Laplace transform, get y of t, and then we will discuss what are the consequences thereafter. Okay.